All right, today we're going to talk about energy in simple harmonic oscillators and simple harmonic motion. So, just as a quick reminder, our ideal system that we're going to use to build all our math is a horizontal spring system where a weight is on one end of a spring. And when we pull it in one direction to extend the spring, then there is a force of the spring pulling back towards the point of equilibrium, a restoring force. And when we pull it in the opposite direction, compressing the spring, there is a force of the spring pushing back against its compression back towards that point of equilibrium. And our restoring force coming from the force of the spring follows Hooke's law, meaning it is proportional in each direction to the displacement that we are changing that spring's length relative to the force that the spring is applying. So we have an equation to express the potential energy stored within the spring. It's from Hooke's law, and it says that our spring potential energy, or U sub S, is equal to 1/2 times our spring constant K times the displacement of that spring squared. And if we simplify our model to assume that we don't have any non-conservative forces, then the spring energy of the system will convert into kinetic energy throughout each cycle and vice versa. And without non-conservative forces, the total mechanical energy of our system should remain constant. So at any point one, our energy should equal the energy at any other point two. Or if we break that up into our different forms of energy, then our kinetic energy at point one plus our spring potential energy at point one should equal the sum of our kinetic and spring potential energies at point two. And because of this, we should be able to figure out a few things at the special points, the points of maximum displacement and our point of equilibrium within our spring's travel. All right, so let's take a look at our horizontal spring system. So we've got five diagrams in this set of diagrams. The first one, diagram A, we've got our mass, and our mass is at our point of amplitude, right? Our point of maximum displacement. So our position X equals, in this diagram, it calls it big X, but I like to use big A for amplitude. And at that point, we have no velocity, right? So our velocity equals 0, meaning their kinetic energy at this point also equals 0. So all of our energy has to be in the form of spring potential energy, which means that it would look like this. It would be 1/2 K, the spring constant, times X or A, whichever one we want to use, squared. So whatever our displacement is squared. And then since that force is accelerating the block in that leftward direction back towards the point of equilibrium, it eventually will point through or a move through that point of equilibrium. And then its velocity is going to be its maximum velocity, V max. At this point, right here, the spring is not compressed or extended. So our potential energy at this point, our spring potential energy equals 0. And all of our energy is within kinetic energy. So right here, all of our energy would be 1/2 times the mass at the end of the spring times the velocity, the maximum velocity squared. And that's at X equals 0, or a point of equilibrium, XEQ. And then because of that velocity moving us through that point of equilibrium, we end up back on the other side where our force is pointing in the other direction. Again, our velocity is 0. So all of our energy is in spring potential energy, giving us 1/2 K times A squared, or negative A squared in this case. But we just square that, the negative goes away. That's our entire energy there. And then, of course, we move back to the point of equilibrium. So this will all look the exact same over here, just moving the opposite direction. And that brings us back to panel A again. This is the same thing as panel A, right? Those are the same thing. So so we can refer to the maximum displacement, as we did in the diagrams, as its amplitude, right? So our amplitude is the furthest we get away from that point of equilibrium. And we can use either A or big X. The diagrams use big X. I'll use big A to represent that maximum displacement. And importantly, note that the maximum velocity will occur at the points of equilibrium. Again, that's panel B and panel D. And then in all of our energy is in the form of potential energy, spring potential energy, and panels A, C, and E at our points of maximum displacement, right? When we're at our amplitude points. So there we're not moving at all. So all of our energy is within spring potential energy. And then all of our energy, once we get to the points of equilibrium, again, that's B and D, is in our kinetic energy, because that's when we have our maximum velocity and our spring is neither compressed nor extended. So we have nothing stored within the spring, no energy stored in the spring. Cool. So let's derive some equations here, which we already kind of did in the last slide, but let's do it a little bit more thoroughly here. So with no velocity, all energy will be potential energy when we're at our positions of amplitude, right? In that case, since all of our energy is in our spring potential energy at our positions of amplitude, or E sub A, our energy at our position A, then we can take and we can use our spring potential energy equation, 1/2 times K times the displacement squared. In this case, our displacement is that A, right? So our amount of amplitude. Good. So that'll be all of our energy at position A or position negative A, our points of amplitude, our points of maximum displacement. And then when we move through our equilibrium positions, at our equilibrium positions or at x equals 0, we're going to have our maximum velocity. So since all of our energy is in kinetic energy at that point, our energy at our point of equilibrium, or xeq, equals 1/2 times m times our velocity there, which is our maximum velocity squared. And since we know that our energy in our system is conserved and is constant over time and throughout all of our positions, that means we can take and we can set our energy at position A equal to our energy at our equilibrium position. So since those two equal one another, we can take the terms they equal, 1/2 mass times velocity max squared, and that should equal 1/2 times the spring constant times our amplitude squared. And we can solve for velocity, for a maximum velocity here. If you want to take a moment and pause, you can solve for that yourself. When you come back, you should get something like this. V max equals our amplitude times the square root of K over M. So our maximum velocity for spring correlates with amplitude. And so long as we assume that K and M obviously are constant, no matter what amplitude we place our system at. And finally, we can then take and generalize this for any arbitrary position x, because again, our total energy, being the sum of the kinetic and spring potential energies, will always be equal to our total energy, the sum of our kinetic and potential energies at any other point, right? So our energy at position x should equal our kinetic energy at position x plus our spring potential energy at position x. And if we break those down into their constituent terms, that means that 1/2 times our mass times our velocity at position x squared plus 1/2 times the spring constant times that displacement of position x squared. Those two together should equal our total mechanical energy at that point. And since, again, the total mechanical energy at any point in our spring system's motion should equal the sum of energy at any other point, then we can set this also equal to our energy at position A and our energy at our equilibrium position. So all those should be equal to one another. And depending on what information we have on hand, we can use one or another to convert between each of these sums of energies at every point. So what we're next going to do is we've been taking a look at horizontal spring systems because they're nice and easy. They only have a single force operating on them. However, vertical spring systems get a little bit more complicated, and then pendulums are kind of go back to being a little bit easier. So we're going to take a look at some real world examples of a vertical spring system and a pendulum, and I'll show you those in just one moment.
Now, unfortunately, a vertical spring system is a little bit more complicated than the horizontal spring system that we've been using to think about energy and that we've been using to make our mathematical models. So obviously a vertical spring system has not just the compression or extension of the spring and the resulting force from that spring to cause its simple harmonic motion, but it has the interaction between the spring force pulling upward and the force of gravity downwards, which means a couple of things. First of all, we can have our energy in three different forms. We're going to have kinetic energy, but we're going to have spring energy, but we're also going to have gravitational potential energy. So we're going to keep track of all three of those things as we go. The second thing, and this is more of a conceptual one, is that when we think about this spring system, if we want to include gravitational potential energy as part of our system, then we have to actually expand out our view of the system, because we can't just include the spring and the mass at the end of the spring, but we also have to include the Earth, because that's where gravity is. And so if we want to use that as one of our conservative forces that contribute energy to our system, then we need to include the Earth. So we're going to take a look, and what we're going to do is we're going to map out a graph and hopefully some equations for this spring mass Earth system. So we've got our mass at the end of the spring, and of course, when it's resting, it will sit at the equilibrium position, right? Now, what we're going to do is we're going to pull this into a state of disequilibrium and let it go. I'm going to pull it down to a point that I've labeled big A for amplitude, and this is the point of maximum displacement, right? And it's going to move through our point of equilibrium, xeq, and will eventually reach its topmost point, which in this case I've labeled as negative A, because it's 1A's worth of distance away from the equilibrium position, just in the opposite direction, right? So we can let it bounce, and it'll bounce from A to negative A. So let's graph out our forms of energy at each position, each of these special positions along its oscillating motion. The first we'll graph out, the easiest, is down at the bottom, it's A, right? So you'll notice that every graph I already have preloaded with a total mechanical energy. And that bar, the total mechanical energy bar, does not change from one position to the other. Because as long as non-conservative forces are not sapping energy from our system and damping our simple harmonic oscillator here, then our total mechanical energy should stay the same over time, right? Obviously, we allow this spring to go to continue moving for long enough. In the real world, non-conservative forces will take away the energy and it will come to a stop. But we're going to pretend as if that's not happening, and over a short enough period of time, the non-conservative forces won't really take away too much energy. All right. So down at the bottom, we can think about a few things. The first is we know that we won't be moving at this point in time, right? So if I let this go, down at the bottom, it will stop, the mass will stop briefly before it reverses the direction and starts going upward. So our kinetic energy, we know, is going to be 0. Great. And on our bar graph, I'm just gonna put a little line there that signifies that our kinetic energy is 0. We can also do something with our gravitational potential energy, which is we can simplify it a little bit by setting the bottom of our oscillating motion to be a height of 0, right? So we don't really care about any height we have above the table or above the floor, because during this oscillating motion, during our simple harmonic motion, we're not going to be using any of that gravitational potential energy from this height down to the table or down to the floor. All we care about is the bottom of our motion, because that's the bottommost height that we'll ever get to. So we can set that equal to 0. And as we know, our gravitational potential energy equals mg times h. And if our h is 0, that means our gravitational potential energy is 0. So we have 0 gravitational potential energy. I'll put a non-bar there above ug on our graph. And that means, of course, that all of our potential energy here at the bottom has to be in that spring energy. Potential energy to spring. So we're gonna table this equation for now, but let's make a graph for that, and the height of the bar for our potential energy of the spring should be equal to our total mechanical energy, since all of our energy we know is in that spring once we're at the bottom of our trajectory here. All right, great. So let's move on and let's go next to our topmost point, to negative A up here. All right, so once we get to the top, we know for our kinetic energy that just like down at the bottom, we will stop moving up here. The mass won't be moving. It'll briefly pause before it starts descending after its ascent up top. So we know that our kinetic energy is 0, and so we can put another non-bar there for kinetic energy, meaning we've got 0 kinetic energy. So let's next think about what our gravitational potential energy is up at the top position. So we know that our gravitational potential energy was 0 down at the bottom because we set our height equal to 0. So what is our height once we get to the topmost position? Well, at that point, we have gone through 1 a's worth of distance to get to x equilibrium, our equilibrium position, and then another a's worth of distance to get to our topmost position. So in total, our height up from our position 0 is 2 a's worth of distance. And so that means that since our height is 2a, that we can use again our gravitational potential energy equation that equals m times g times our height. In this case is 2a. So our gravitational potential energy is 2mga. And we can take and we can put a bar on our bar graph for ug. I'm going to draw a bar graph for ug that is not going to go all the way to the top of, is not going to match in height our mechanical energy bar. And you may want to think for a moment about why that is. So it would be a good idea to pause, consider, and then come back once you've thought about it. And hopefully the conclusion that you reached is that while we consider this the least amount of stretch that we end up using in the spring, it still is some amount of stretch. The spring has been displaced some amount from its original length. If we look at its original length like that, this is its natural length of the spring. But once we get to 2a, once we get to a height of 2a, or our maximum displacement in that topmost position, we have stretched the spring some amount. And so there is some amount of spring energy that's stored in here that's still part of our system. So I'm going to leave a little bit of headroom between our gravitational potential energy and the total mechanical energy. And the remainder is there should be a little bit of spring energy that is stored within this system as we go. All right? So what we're not going to do yet is we're not going to put an equation to our spring potential energy for this topmost position just yet. All right, so let's now consider our equilibrium position. So obviously the main thing over at equilibrium position is we know that we're going to have our maximum velocity. So let's think about kinetic energy first. And we know that our kinetic energy equation is 1/2 mass times velocity squared. So our kinetic energy should be 1/2 times the mass at the end, times the mass of our spring system times our maximum velocity squared. And that will give us some amount of kinetic energy. I'm going to hold off on drawing that bar graph for kinetic energy just yet. Let's first consider our gravitational potential energy before we do that. So our gravitational potential energy, we know that our height here is we've gone up from a height of 0, up a's worth of distance. So our height here is a, so that'll be mga is our gravitational potential energy. And if you compare that to our gravitational potential energy up at our top position, we know that it's 1/2 of that. So I can make a bar graph over here that should be about 1/2 of the bar that I gave to gravitational potential energy on that top graph. And finally, we've got our problem child, the spring potential energy. And we're going to table that for one more moment. Let's instead just consider that it is going to increase from this right here. And we don't yet have an equation to figure out how much it increases from our top position to our equilibrium position. So let's just kind of eyeball it as a little bit more. All right, so I'm going to draw a bar that is slightly larger than that one, though certainly not as large as our total mechanical energy. I'm going to give it something like this. And then, at least now that we've drawn that, even though we don't have an expression for that just yet, we can now draw a bar graph for our kinetic energy, because we did have an expression for kinetic energy, but we don't know what our maximum velocity is just yet. So we kind of have to eyeball what our bar in the graph will be, right? And what we do know is that if we add our 3 energies together, they should match the height of our total mechanical energy. So I'm going to kind of eyeball some height for kinetic energy that may or may not, if we added these three bars together, reach a height of the total mechanical energy. The way I drew them is probably a little bit bigger than the bar for the total mechanical energy, but close enough, all right? So now we've got bar graphs for each of these positions, right? And again, this is a little bit more complicated than our horizontal spring system, because where in that, all we had to worry about was spring energy converting to kinetic energy, then back to spring energy as we went back and forth along those oscillations. For a vertical spring system, we've got three different energies, right? We've got our kinetic, our gravitational potential, and our spring potential energy. And our spring potential energy doesn't really go away throughout this. And so our kinetic energy is whatever's left over from the spring potential energy and from the gravitational potential energy once we hit any of these points that aren't the points of maximum displacement, in our graph being A and negative A. So let's consider what terms we will put here for this spring potential energy. And why don't you take a moment to consider what those should be, and maybe try to come up with an equation, or at least ponder conceptually what we're going to use to figure out what our equation will be for U sub S for our spring potential energy. All right, you may have realized that unfortunately, we haven't yet put down the information that we need to determine what our spring potential energy is at any point. Because remember that our equation for spring potential energy is that it's 1/2 K, the spring constant of the spring, times X, the displacement of the spring squared. But the displacement of the spring isn't based on the heights we've been using in the past. So I'm going to get rid of those for a second. Those are a useful metric for us to determine our gravitational potential energy. But unfortunately, our spring potential energy depends not on how far we are from the bottom, but how far we are from the top. And the top not being our topmost position, but instead being the natural length of the spring. And so, if I were to hold the weight up here at the natural weight of the spring, it would rest about here. So we can call that our L naught, meaning the natural length of our spring mass system if the spring is exerting no force. And the spring is holding no potential spring energy for the system. All right, so that means that actually, if we determine our spring potential energy, we need to think about our displacement from this position in order to determine what our spring potential energy is. So to make this easy, what we're going to do is let's judge everything by this position right here. And what we'll call this is the change in our length, right, which is our displacement of the spring. And we'll call that delta L EQ, right? I can't use XEQ because we already defined XEQ as 0, right? That's our 0 position for the mass. And as it moves in one direction, it's going positive, the other direction is going negative. Or if we think about height, we already defined that position in terms of height as a height of A, right? So this position we now had to define in a third sense. In this sense, we're using the reference of our natural spring length, natural spring mass system length, right? Which again, our mass spring system will sit here if there's no force of the spring and no potential energy stored in that spring. So when we bring it down here, we have a stretch of that much. And that means that our spring potential energy, we can find an equation for, because it's 1/2 K, the spring constant, times the length of stretch for this position, which is delta L EQ. Delta L EQ is what we chose to call it, or what I chose to call it. We could have called this B, we could call this Y, we could call this anything. Chose to call it delta L EQ. But whatever that distance is that would stretch from that natural spring length, that is our X, right? That's our displacement of the spring. And then we do want to square that. So our spring potential energy here should be U sub S equals 1/2 K times whatever this length is, whatever this change in length is, squared, all right? So 1/2 K delta L EQ squared. And then things actually get a little simpler from there. Now that we've defined our reference of L naught, now we need to think about, for if we go to our top position, well, how much have we stretched the spring in this top position, right? And we've stretched it this amount right here, going to negative A. Well, what is that? That's if we stretch from LEQ and then we subtracted A away from here. There's A's length right there. So this distance right here is just delta LEQ minus A. We've already got that negative A. We know that's negative A's worth of length, and we just have to add that to our delta LEQ. So our spring potential energy up at that top position is just going to be 1/2 times K, our spring constant, times our new stretch length, which is delta LEQ minus A, and that's squared. All right? So, since we're subtracting A from that, obviously this is going to be shorter, and we're going to have less spring potential energy at this point than we had at that point. And that makes sense because our bar graph's going to be a little bit smaller there than it is down there. All right? And finally, our last point is all the way down here, and you probably already know what this is, but you might want to take a moment and pause the video to think about what's our new length, how are we going to express it in the terms we've put so far. And if you do that, you probably will come to the conclusion that, well, what took me to stretch delta LEQ to get here, and we had to stretch another A's amount to get down there. So this position right here, relative to our natural spring length, is delta LEQ plus A, right? And that means that then we can plug that into our spring equation down here, 1/2 K times delta LEQ, that equilibrium length of stretch from our natural springs state, plus A squared. So look at that. This is way more complicated than a horizontal spring system, right? And of course, that's why why when we built up our math, we used the horizontal spring system instead of this. But this is all doable, right? As long as we are meticulous and keep our thoughts in order in terms of the concepts that are happening here, right? So again, this is difficult because we have 3 different forms of energy that we're converting between here, and one of them doesn't ever disappear throughout any of our positions within this spring mass Earth system, right? Our spring energy will always have some amount in there because we're never going to get to a point of 0 stretch of the spring, all right? So, I hope that's a little bit clear. We're going to be playing with this moving forward. Thank you. That is our most complicated system. So things can only get simpler from here. And speaking of simpler systems, hallelujah, let's take a look at our pendulum system. So just like with the vertical spring system, this really is a pendulum Earth system because gravitational potential energy is the form of energy in which our mechanical energy for the system will be stored, right? So down at the bottom at our equilibrium position here, when our string makes a 0-degree angle with the vertical, then all of our energy equals energy at EQ equals kinetic energy at EQ plus our gravitational potential energy at EQ. But if we set this height down here to equal 0, right, which we're only going to go upwards from there, then this term goes away. And so our energy at our bottommost, our equilibrium position should be 1/2 times mass times our maximum velocity squared. This is the fastest we'll be moving is down the bottom of this curve, right? We should be moving fastest right there at that point of equilibrium. All right, so now let's think about what happens when we get to the top. So once we get to the top, we're going to reach some position, and that position is some height h above our equilibrium position. So our h equals, we're going to call this a big capital H, okay? So that's the maximum height that we get up to. And if we think about our position, our energy over here, our E at h, at our point of maximum height over here, or our point of maximum displacement, that should equal our kinetic energy at h plus our gravitational potential energy at h. But at that point, that is where our pendulum will stop moving and begin to swing back in the other direction, right? So our kinetic energy here is 0. And that means that our total mechanical energy at H is just m times g times whatever that height H is. All right. If we wanted to, we could find H in terms of the angle that the string is making from the vertical, but we're not going to do that right now. Okay. And then again, like any of these springs, like any of these simple harmonic oscillators, our energy at one point will equal our energy at any other point, right? Our total mechanical energy should be conserved throughout this oscillating motion. So our energy at point EQ should equal our energy at point H, right? Whatever gravitational potential energy we have at this point, there is no kinetic energy, and we are unlocking that gravitational potential energy to become kinetic energy once we swing through that point of equilibrium. And so that means we can find our maximum velocity here, because our maximum velocity squared times m times 1/2 is our energy at our point of equilibrium, and that should equal our energy at our point H here, or a point of maximum displacement, and that will equal mgh. So we cancel out our m's, and as long as we know our h, or as long as we know the length of the string and the angle the string is making at our point of maximum displacement, then we can find our maximum velocity. And we're going to practice that today, as well as practice taking a look at our other types of simple harmonic oscillating systems. Thank you for learning with me.